which is entitled, it's really entitled Continuous Random Variables, but we're going to focus on one major example of that called the normal distribution, sometimes called the bell-shaped curve. This is the shape of the bell. And this is the introduction to it, which will be basically, you'll be able to, hopefully after the next 20 minutes or so, you'll be able to solve problems in the chapter by merely looking at a picture that should make, you can do the problem by sort of commonsensical, intuitive approach. And if you want to fine-tune the method, we'll have to go to another formula. But you can get the main part of the answer just by looking at the problem graphically and understanding what the question is trying to get you to do. Before I explain the mathematical, a little more mathematically advanced normal distribution, I want to point out to you that it's really one small step away from a simple histogram, which you learn about in chapters 2 or 3. And you probably learned about it in 5th or 6th or 7th grade when you learned about bar charts and histograms and things like that. So let's start out with a concrete example. Let's say I took a very large census. This is of all the American males. So X equals male weight. And I asked everybody their weight. Male weight. So we're talking about, let's say, 100 million adult males between 18 and 75. Healthy, we're not talking about people who are particularly diseased in any way. And then we took all those 100 million numbers. 100 million numbers fill in like 20 phone books or one DVD or something. 100 million numbers. And I logically, in order to understand them, I can't read through 20 phone books to figure out stuff. You have to basically summarize it. And of course, summarizing, you might want to get the average. You might want to calculate the standard deviation. It's a good way of summarizing the data. But another, even more basic way of summarizing the data is by putting it into a picture. So you say, okay, in order to make a picture, what kind of picture should I make? And you decide to make a histogram. In order to make a histogram, you got to make intervals. So you say, I'm going to do the lowest number, let's say 80, so 80 to 90, 90 to 100, 100 to 110, 110 to 120, 120 to 130, 140, 150, 160, 170. And there's really no limit to go 180, 190, until we run out of numbers. Now, if somebody's 400 pounds, I wouldn't call that a healthy person. So let's say it stops at 300 pounds, at 320, I don't know. Okay, the point is, now how many adult American males weigh between 80 and 90? You think anybody who's an adult, normal, healthy, can weigh 80 and 90, 85 pounds or something like that? Well, if I took a sample of like 100 people, would I find any male who weighs 85 pounds? Probably not. But if I took a sample of 100 million people, would I find a bunch of like jockeys, for example, or people who are just very short and very skinny, but normal? So how many people are we going to find? 725, 416. I mean, it can't really, but it won't be zero, and it won't be a large number, but it's going to be a small percentage. Let's say 1/4 of 1%. That'll have. I'm just making it. Of course, this is the percentages. So make a little bar here. How many between 90 and 100? Maybe 2% of the population. How many between 100 and 110? Maybe 7% of the population. Between 110 to 120, maybe 12. Keeps getting higher and higher until what point? At what point would you start going down again? When you reach which number? The average. Most people are average, so the highest bump, the highest percentage should be the average. This is for you, mate. And let's say the average was 140 pounds. So we have 140, and this starts going down, going down. So it's not surprising that you get a picture that eventually we're going to be called the bell-shaped curve. You get a picture that looks something like this. So when you make a picture like this, we're really talking, when we see a picture like this, we're really talking about a picture like that. Now, but to even make the two pictures closer together, imagine instead of breaking people down to 10 pounds, I decided to break the intervals down to 1 pound. And how many people weigh between 110 and 111, 111 to 112, 112 to 113, 113 to 114, 114 to 115? What would the picture look like in that case? Let's try to break it down. There are going to be two changes. If I break this up into individual, 111, 112, 113, 14, 15, 16, 17, what's going to happen to the picture now? I want you to tell me two things that are going to change. One thing I've thought about all my life, and one thing I just realized for the first time this term, there are two changes to the picture. Yes, Nate?
Just become more of a gradual
Right, because exactly right. You're going to get 110 is close to 111, and close to 112, 113. So the picture you're going to get is something like this. Okay? You're going to get a picture like that. And if it broke it down to the nearest ounce, so again, you'll be still, how many people weigh between 112 pounds and 13 ounces to 112 pounds and 14 ounces? Is there anybody in the whole United States who weighs between that particular, probably a few hundred people? Because we took 100 million people, so it's an incredibly large number. So you realize that if you keep doing this, you're going to end up with a curve that, again, eventually when you see that, if you keep doing this smaller and smaller and smaller, you take it to the limit, and then approaches zero when you're technical about it. You're going to end up with a smooth curve. Eventually it's going to be just from here to here, a smooth curve, where if you look under a microscope, you'll see there's little steps there, but unless you look under a microscope, it's going to look like a smooth curve. So when we see a picture like this, what we're seeing is how many people weigh between 113 pounds and 4 ounces. Basically, it's a whole bunch of little tiny skinny bars that make up a big histogram. Now, but that's I've been telling my class for 30 years. Now there's something else I realized. What else will happen to this picture besides getting the little bumps will get a little more gradual, as Nate said. Yes, Dow.
The highest point wouldn't be as high. It would be like a lot lower.
Okay, your intuition is excellent. It took me 30 years to realize that, but I guess you realize it because of back then. Okay. If this number here, let's say for argument's sake, there was 15% before, but now we break it up into little categories. How much would be in every category? Since there are 10 categories, you've got to be 1/10 as many people, so the percent has got to drop down by 1/10. So instead of going from 15%, this might be 1.5% in this category, 1.36% here, 1.7% here, 1.8. It's going to drop down by a fraction of 10. And if you break it another fraction of 10, it's going to drop down even more. So you might think when you're all finished, you're going to get a flat line, because everybody's going to be practically, if you make enough categories, you're going to have, the highest category might be 0.00001%. So it's going to look like a flat line. And that's what I was concerned about when I realized that problem in the shower a few months ago when I was teaching it to my Stat 1 class. But I realized there's a solution to the problem. Anybody know what the solution is? The answer is, just keep changing this. Who says, if you're going from 0 to 20%, make it by every time you do one of these conversions divided by 10, just change this by a factor of 10. So the picture keeps its relative shape. You've got to look under a microscope to see it, but if you look under a microscope, you're going to see the original picture. So that's a good point, and I think that's a good answer. Got myself on the back. Okay. The bottom line is, when you see a picture like this, you have, don't think of it any more, it is more complicated, but you don't have to think of it as more complicated. Now, if you add together this plus this plus this plus this plus this, what are all those percentages add up to? Raise your hand if you want to answer the question. Back. It's got to add up to some, got to be 100%, because we're taking everybody into account. Okay, when you get your name out, you'll... Okay, now likewise, if I took together all these different little, again, they're almost invisible because they're all very, very skinny categories, and add them all together, what are you going to add up to? It's just a histogram, going to add up to 100%. Now, what about the area? How much area is there between here and here? Well, technically speaking, this bell-shaped curve never really ends. It's asymptotic, it goes down lower and lower, but practically speaking, after about a certain, it goes down to very close to the bottom. The area from here to here is literally 100% of the area. So it turns out that since these categories are proportional to the area, for example, if it covers half the area, then it covers half the percentage. If it covers a third of the area, it covers a third of the percentage. So we have to, without getting into too complicated a discussion, the bottom line is, if you want to figure out the probability, which is what the whole chapter is all about, the probability of, let's say, somebody's weight, remember x equals male weight, is lower than, let's say, 140. Let's put down the average was 140. Let's put down that the sigma was 15 pounds. Okay, what is the amount of spread from person to person, sigma? What's the chance somebody weighs less than 140 pounds? That problem can be basically calculated by getting the area under the curve. I mean, the way to get it directly is how many people are less than, these guys were less than 140, it's like 12% here, and 10% here, 9% here, and 8% here. Add them all together, and if the curve is symmetrical, which I haven't mentioned till now, but that's the assumption that the bell-shaped curve is symmetrical, you cut it down the middle, the left side and right side are mirror images of each other, how much is going to be below the average? What's your intuition tell you? How much is below the average? Yes? 50, half. So this should be, the answer to the question should be 50%. How many people weigh more than 140 pounds?